In this video, we're going to take the formula for the confidence interval of the population mean that we derived in the last video, and we're going to go through an example of interval estimation using that formula. All right, now I'm going to read off the problem. I'm going to read it off twice. First, I'm just going to read it, and the second time, I'm going to read through it and pull out the important pieces of information. And then we will work through the example. All right, so this says, suppose you are watching a baking show and you begin recording the number of cookies contestants are making in a single batch. You determine the average is 26.31 with a standard deviation of 2.97 based off of a sample size of 45. And then it tells us to find the 95% confidence interval for the population mean for cookies, or the number of cookies made in a single batch. So let's go through that again, and this time pull out the important pieces of information. All right, so suppose you're watching a baking show and you begin recording the number of cookies contestants are making in a single batch. You determine the average is 26.31. That's obviously important. That's the average. And this would be our sample mean, so X bar. So X bar equals 26.31. Then it goes on to say with a standard deviation of 2.97. So this is going to be our likely our sample standard deviation. Now the formula gives us tells us to use sigma, which is the population standard deviation, but as long as n is greater than or equal to 30, we can still use this this formula and estimate sigma with s. All right, so we can estimate sigma with s and still use the z distribution. That's not going to be the case later on, as we're going to see, but for now, as long as n is greater than 30, we can use the z distribution as long as that's true, right? And we can substitute sigma, or substitute s for sigma. All right, and then it's based on a sample size of 45. All right, so our sample size is greater than 30, so we're in the clear to use the sample standard deviation versus the population standard deviation. All right, and then finally, we're doing this at a 95% confidence interval. Or 95% confidence level, we could say. So now we have all of the important pieces of information for us to go ahead and start going through this example. All right, so as we set this up, all right, we're going to start with our sample mean, 26.31, all right, plus and minus our critical value, so that's our z. So our z is z alpha divided by 2. If we're working with the 95% confidence level, right, that means that our alpha is 0.05, and we're going to take that 0.05 and we're going to divide that by 2. We'll work through that in the next step. All right, then we're going to multiply our critical value by our standard error. Our standard error is our standard deviation over the square root of our sample size. So in this case, 2.97 is our standard deviation and 45 is our sample size. So we have 2.97 over the square root of 45. So we're going to condense this down a bit, all right? So we're dividing 0.05 by 2 here in our critical value. So we're going to make that 0.025, and then we will go ahead and do our calculation for that standard error. That's going to give us 0.44 And then we can continue on, and we don't do anything to the sample mean. There's nothing to be done at this point. All right, so once we get to this point, we need to find that critical value. All right, we're looking for Z 0.025. We've already looked at this. We should know that this is 1.96. So we could have either gone to our standard normal distribution chart and looked for that 0.025 in the probability section and followed it out, found negative 1.96. And then of course, since we're adding and subtracting, it doesn't matter if we put it in as a negative or a positive, right? Or we could have just pulled it off of that list I gave you. All right, so then we're going to multiply our critical value and our standard error together. And we're going to get 0.86. So the last thing for us to do is to just add our, we're going to talk about this in a bit more detail later, but this term, what we're adding and subtracting from the sample mean is what we call the margin of error. You don't need to, we'll write all that kind of information down later, but that is what it's called. So all we need to do now is subtract our margin of error from our sample mean to get our lower boundary and add it to the sample mean to get our upper boundary. So once we do that, we're going to end up with our 95% confidence interval, right? Our lower boundary will be 25.45. And our upper boundary will be 27.17. Now, in the last video, we talked about how when we were just looking at our formula, that the probability that the population mean falls into an interval constructed using that formula, if we're doing it, is, we looked at the 95% confidence interval specifically, so where we had 1.96 in there for the Z. We said that the probability that we said that the probability that the population mean was in an interval using that formula was 0.95, right? That was the interpretation or just a statement we could say, and that was true. However, once we apply data to that interval estimator, that is no longer true, right? Because although we don't know the population mean is a specific value, right? So once we actually have an interval, right? Once we've actually got this interval estimate, then that saying is no longer true, right? Because even though we don't know what the population mean is, it either is or is not in this interval, right? So let's say that the population mean was 26, right? In that case, it is in the interval, right? The probability that 26 is in this interval is not 0.95, it's 1, right? Because it just is in the interval, right? If it was 28, right, then the probability that it's in the interval is 0, right? Because it's not, right? It's not in that interval. So the way we're going to interpret these is a little bit different once we actually have an interval estimate, once we've actually estimated this interval, right? So we're no longer going to be able to say something useful about the probability. Instead, we're going to rely on this idea of confidence, right? So the way we'll say this, and this is the interpretation for this specific one, I am 95% confident that the population mean is between 25.45 and 27.17. Right, so that is how we would interpret this. All right, just in a general format, we could say I am 100 times 1 minus alpha % confident, or so just whatever your confidence interval was. If it was a 99% confidence interval, you'd say I'm 99% confident. If it was 95, I'm 95% confident, 90% confident, so on and so forth, right? That the population mean is between the lower bound and the upper bound, right? So that is how we would say that. We could also kind of, ideally, we would make it more applicable to the exact problem that we were looking at. So in this case, we could say I'm 95% confident that the population mean for the number of cookies made in each batch is between 25.45 and 27.17. All right, something along those lines. Right? But that is our confidence interval. So we will move on to the next thing. All right, I suppose this, technically I should have said that it was the confidence interval when we're using the z distribution. So this method of finding our confidence interval, we can do this when we can use this method when one of two things is true, right? Either sigma is known, so the population standard deviation is known, or when the sample size is greater than or equal to 30. So one of these two things has to be true in order for us to use the z distribution and to use the method we have just looked at, that we did an example for in this video and that we derived in the last video, right? But what if some of these things aren't true, right? We kind of think of these as assumptions. What if these assumptions aren't true? Well, looking at our first one up here, sigma is known, right? This isn't a very realistic assumption, right? The reason is because what we're doing in this section, right? We are creating an interval estimator for the population mean. So that implies that we do not know what the population mean is, right? If we don't know what the population mean is, it's very unlikely that we know what the population standard deviation is, right? Because to get our population standard deviation, we first have to have our population variance. And to get our population variance, we have to know the population mean, right? If we think about all the way back in chapter 4, when we were calculating the population variance, the formula was the sum of x minus mu, or xi minus mu squared divided by capital N, the population size, right? So if we need to know the population mean to calculate the variance, and we need the variance to find the standard deviation, right? And by kind of definition of us wanting to do one of these interval estimates, we don't know the population mean, it's very unlikely that this one is true, right? It's very unlikely that sigma is known, right? What's much more likely is that our sample size is greater than or equal to 30, right? That's gonna, to be honest, that's gonna happen pretty frequently, right? So that's a pretty safe bet. But there are going to be circumstances where that's not the case, right? That our sample size is not greater than or equal to 30. So what are we going to do in those cases? All right, in those cases, all right, we're going to use something called student's t distribution, right? But I'm going to kind of formally write this up here before we jump into that. All right, so if sigma is unknown, n is less than 30, Right, so that last thing is kind of long, but once again, just from the top, if sigma is unknown, n is less than 30, and we can assume that the sample is drawn from a normally distributed population, then we can use student's t distribution. All right, so most of the time we're going to focus on these first two things. All right, sigma being unknown and the sample size being less than 30, and we're going to kind of just assume that this last assumption is true. However, for homeworks, tests, and things like that, most of the time I'm not going to explicitly say this data comes from a normally distributed population, but this is a very important assumption. All right, the reason for this is because when we have a sample size greater than or equal to 30, then the central limit theorem kicks in, and no matter what the distribution of the population data that our sample came from, if we have a sample size greater than or equal to 30, then the distribution of the sample mean is approximately normal, right? That's the first property we get when we talk about the central limit theorem, right? That's what allows us to standardize our sample mean. That's what allows us to derive that interval estimator, right? If our sample size is less than 30, we can't just assume, then the central limit theorem doesn't kick in, right? And so unless the data that we are using, right, if the sample data we have, unless it's drawn from a normal distribution, right, then it will not have, the sample mean will not have a normal distribution. All right, so I'm going to repeat that once again. All right, so if we're looking at something, all right, and the population data is not normally distributed, all right, if we take a sample that's less than 30 and we calculate the sample mean, right, the sample mean will not have a normal distribution. That means we cannot use we can't standardize, we can't use the z-score, right, we can't use all of that kind of stuff, right? So we can't do anything that we've been doing if the data is not from a normally distributed population, right? However, if the population is normally distributed, then we can still use it if n is less than 30. We just have to use this t distribution, right? Again, that assumption we're not going to worry too much about, but it is an important factor in what we're doing. All right, so now let's start talking about how we're going to do interval estimation with these smaller sample sizes. All right, so we're not going to take the time to derive the whole thing again, partially just because we don't have to. It's not going to be that different. Really the biggest difference, we're really going to use the same bones that for the interval estimator that we did previously. The big thing that's changing is we're using a different distribution. All right, so instead of using the z distribution, the standard normal distribution, we're going to be using what's called the student's t distribution. All right, so the student's t distribution is different from the z distribution in one big way. For our purposes, at least right now, what we're going to be using t alpha divided by 2, right? That's pretty similar to our z, right? We've been looking at z alpha divided by 2, all right? The big thing is that we're going to have one additional thing that we have to take into consideration. Right, so you might see this written as, or you will see this written as t alpha divided by 2, comma df. Right, so this is all in the subscript. This is just telling you how to find that t, that critical value. You're not supposed to multiply these together, add them together, or anything like that. All right, so alpha divided by 2, that's going to work just like it has in the past. The DF stands for degrees of freedom, right? And the degrees of freedom are equal to n minus 1. All right, so what these degrees of freedom are doing is that they are essentially penalizing a small sample size. All right, we're probably gonna, the more you play around with these, the more you're gonna see this, but generally speaking, the smaller the sample size, the larger the critical value, right? And the larger our critical value, if we think back to what we've already done, right? If our critical value gets larger, that means that our margin of error gets larger, the thing that we're adding and subtracting from the sample mean, which means that the interval we're calculating gets wider, right? And that's kind of the opposite of what we want, right? We want as narrow of a interval estimate as we can get, right? But if we don't have a large enough sample size, that's going to kind of cast some doubt on the accuracy. And so it's going to kind of, that's what that degrees of freedom is there for, right? It makes, it kind of gives the error more weight, so we kind of properly take into account the fact that we don't have a very large sample size, or you could think of we don't have a lot of evidence for what we're trying to say. The less evidence, the more weight we're given towards any kind of dissimilarities, any error, so that it's going to make that confidence interval wider. All right, so that's what our degrees of freedom are doing. All right, and one last thing before we talk about how to use, right, our t-distribution chart and find these kinds of things. One thing I want to note is that as n goes to infinity, right, as n increases, as the sample size increases, the t-distribution goes towards the z-distribution. Right? Ultimately, what this really means is that the t-distribution is an approximation of the z-distribution. It is approximated, and the approximation there is dependent on that degrees of freedom, right? How large the sample size is, that determines how closely the t-distribution resembles the z-distribution. Right, but as the sample size goes to infinity, the t-distribution becomes the z-distribution, right? And this is going to become important in just a moment, right? Or I'll explain why this is useful, I guess. It is important, but I'll explain why it's useful in just a moment. All right, so this is how we're going to read that t-distribution. All right, first, the t-distribution, it is the 4th page on that PDF of statistical tables. So once you get past the 2nd page for the standard normal distribution, that next one is the t-distribution. All right, it's going to look slightly similar, but also not identical to the z-distribution table. All right, the reason for this is because, well, actually really it's just kind of flopped around a little bit. In the z-distribution, the middle section are our probabilities. That's not the case with our t-distribution. For our t-distribution, the numbers in the middle, those are our critical values. Those are our t alpha divided by 2 comma degrees of freedom, right, whatever it is we're looking for. Right, along the top row, this is where you're going to look for that alpha divided by 2. All right, so this is what it's going to look like. It's going to have just a bunch of t's up here with subscripts. So T 0.05, T 0.025, so on and so forth. There's going to be more than 3 on there, right? There's going to be quite a few. This is where we're going to look for that T alpha divided by 2. So whatever that is, that's where we need to find it. If, say, for instance, we're doing a 95% confidence level, that means alpha is 0.05. Divide that by 2 to get 0.025, and then we look for that up here. All right, and so that would tell us that this is the column our critical value falls in. All right, the first column gives us the degrees of freedom. All right, so it's going to start with 1, and it's going to go to infinity. All right, and it'll go 1 through 30, and then it'll start skipping, and until like, I think the last number before infinity is 120, right? But when we look for our degrees of freedom. Let's say our degrees of freedom were 26, right? So we have a sample size of 27. N is 27 minus 1 gives us 26, right? That would tell us that our critical value was in that row. All right, where that row and column intersect, that's where our critical value would be. All right, now they do have this row that is the infinite degrees of freedom. All right, this is important because what we can do with this is we can use it to find our z's. All right, so instead of having to go and look in our z distribution chart, look through all of those probabilities to try to find the correct one, and then when we get to, say, the 90% or 99%, and we're doing a confidence interval, having to try to figure out what the value should actually be because the probability isn't on there. Instead, we can just come to our t distribution. All right, so if we're doing the 99% confidence interval, we'd go up here, we'd look for 0.005, so that's our alpha divided by 2, and then we could go all the way down to the last row of our chart, and we would see where that column and that last row that starts with the infinite degrees of freedom meet, that we have 2.576, right, which is what we put on the board in the last in the video where we covered those confidence levels and those alphas and their z alpha divided by 2's. All right, so it's just a quicker, easier way to find those instead of having to try to memorize them or anything like that. All right, so all that said, let's go ahead and put up the formula for our confidence interval when we're using small sample size. All right, so our 100 times 1 minus alpha percent confidence interval for the population mean with n less than or equal to 30 is equal to, or is, I guess we could really say, all right, sample mean plus or minus t alpha divided by 2 degrees of freedom, and then we have our degrees of freedom there, times the standard error, which is s over the square root of n. So that is our formula. All right, so this video is getting a little long, so we're going to go ahead and stop there. In the next video, we're going to do an example. We're actually going to use this formula, and then we'll also talk a little bit about precision and sample size. I'll see you in the next video.